Bonding review. This is page 24 in your packet. By all means, I will open the chat if I ask a question and you want to type it in versus unmuting yourself. Totally up to you. So bond types. You have three choices here: ionic, nonpolar, and polar covalent. Ionic, if you remember, would be like if we were to take off somebody's hand when we're handshaking it, taking that electron. Nonpolar would be a normal handshake, and polar covalent would be that weird handshake where somebody tries to pull you towards them. So a transfer of electrons would be taking off the arm, so that would be ionic. Electrons being shared would be a normal handshake, so that would be nonpolar covalent. And when they're not shared equally, that's somebody pulling too much. We can imagine the one pulling too much is going to be the one with the higher electronegativity. So if it has a higher electronegativity, those electrons are going to be closer to that atom when the bond is formed. If we have two pairs of electrons, for example, two hydrogen atoms bonded together, that is the same as a single bond. If we have two pairs of electrons, this would be a single bond. Two pairs is actually this, and that would be a double bond. Read the questions. And if we have three pairs of electrons, that would be like that, and that would be a triple bond. A blank is a non-bonding pair. We call that a lone pair. The blank rule, or the octet rule, is the principle that an atom bonds in order to fill its outside shell with 8. Hydrogen does not do this. Hydrogen only needs one bond. Beryllium is fine with 2 bonds and no lone pairs. And boron is fine with 3 bonds and no lone pairs. An electron in the outside shell, we call that valence electron. That's something that we need to make sure we know how to find. We use the periodic table in order to find the valence electron number by looking at the group. You're not going to believe this, but I did not bring a periodic table, so let's see how much I can remember. A non-metallic element, group number. So if it's in 5A, it has 5 valence electrons. 6A, it has 6, 7A, and then the noble gases will have 8. Atoms of blank, atoms of hydrogen, as we said, only bond once. 2 electrons is all they need for the octet rule, because all they have is that s orbital to deal with. A blank molecule is the result of electrons shifting. That is a polar molecule. A polar bond is when the electrons shift in the bond. A polar molecule is when there is a pool of electrons to one side of the molecule, and there's not an there's an uneven pool. They don't cancel each other out. Blank are substances that have the same general formula but different atomic arrangements. Those are isomers. Remember, we did the one where you had the straight chain of carbons, and then we did the carbons where we had 3 carbons in a chain and 1 coming off, the center one. These would be isomers of each other. I'm not going to bother drawing all the hydrogens and stuff. Molecular shape, you have those answers to use. A molecule has a blank shape if the central atom is double bonded to one atom. For example, carbon and oxygen. And we have 2 other atoms it's bonded to. That is a 1, 2, 3. So we would call that sp2. sp2 hybridization is for a trigonal planar molecule. Imagine a central atom with 3 atoms attached to it. So I'm just going to use this guy to start off with, even though that's not something that's real there. Let me see if I can adjust this a little bit so I can make sure I get all of this on there. So if there are no lone pairs, again, sp1, P2. So that would be what we would call trigonal planar, just like before. One lone pair, 1, 2, 3, 4, so S, P1, P2, P3. That would be a tetrahedral arrangement. We're looking for the molecular shape, so that would be trigonal pyramidal. And here we have 1, 2, 3, 4, 5 things. SP1, 2, 3, D1. So the arrangement there would be trigonal bipyramidal. But since we have two lone pairs here, that's going to be T-shaped because we're looking for the molecular shape, not the electron arrangement. T-shaped. Imagine an atom with 4 atoms attached to it. So we will do this. Again, while these angles look like they are what you would call 90 or something like that, in reality they're 109.5. So here we have S, P1, P2, P3, S, P3. That would be tetrahedral. With one lone pair, again, the arrangement is going to be trigonal bipyramidal. But since one is a lone pair, that's not the shape. The shape of this would be seesaw. And that is sp3d1. 2 lone pairs. Again, sp3d2. And the arrangement would be quadrilateral, octahedral, or what we call square bipyramidal. This case, since we have these 2 electrons here, that's going to end up being square planar for the shape of the molecule, though. Square planar. If a molecule only has 3 atoms, its shape can be 2 things. It could either have 0, I'm just going to draw circles for atoms. It can either have 0 lone pairs, which would be trigonal planar, 120 degrees for the angles there. Or if we have 1 lone pair, that would be trigonal pyramidal. Questions for page 24? You can either type them or unmute yourself and ask. No? It's bond angles now. Bond angle for a linear molecule, that's a straight line, that's going to be 180. Bond angle for a trig plane is 120, and tetrahedral is 109.5. If we have that tetrahedral arrangement and we replace one of those atoms with a lone pair, that's going to go down lower. So trigonal pyramidal would be 107. And then if we took another one away, it's going to push that bond angle down even more. So that would be 104.5. That's what we used. According to the VSEPR theory, the strongest electron pair repulsion is between lone pairs. So basically, since these lone pairs are closer to the central atom, that's going to have a bigger repulsion versus having the atoms having these bonds that are longer. The weakest would be bond-bond because they are outstretched. If all electron pair repulsions were the same, CH4 and NH3 would both be 109.5, but NH3, since it has that lone pair, is less. It's 107. And that's because the nitrogen atom's lone pair is closer to the nitrogen atom, and it decreases the bond by 2.5 degrees. In the Lewis structure for SiCl4, let's go ahead and draw that. Center atom is Si, based off of uniqueness. 4 Cls, 2, 4, 6, 8. We're going to have 32 here, I think. See if we have any extra. silicon. Silicon is 4, and chlorine is 7 each for a total of 28. That's 32. So the central atom is S. The number of valence electrons is 32 total. For CHOF, we have 4, 1, 6, and 7. That is 10. What am I doing here? We got 13, 14, and 18. There we go. C is in the middle because of the honk rule. Carbon likes to form 4 bonds. H, F, and a double bonded O. 2, 4, 6, 8, 10, 12, 14, 16, 18. So there's our total. Again, the central atom is C. The number of valence electrons is 18. What word refers to a structure where the position of the atoms remains the same, but the distribution of electrons differ? Where the position of the atoms remains the same, but the distribution... Again, that's going to be a polar structure. We're pulling the electrons to one side. CH2Br2, we draw that, C in the middle again. We have 4 bonds, 0 unshared pairs, so that would be sp3, which it shows right here. That would also be tetrahedral. For SeF4, we have extra electrons when we add all those up, so we're going to put those on the central atom if everybody else has the octet. And that's going to be sp1, p2, p3, d1, as we can see here. And that's going to be seesaw.
Don't you think that 25 would be resonance is what they're trying to talk about and not polar?
Oh, well, let me read it. Good call. The word refers to a structure where the position of the atoms remains the same. The distribution of electrons can differ. I would accept polar for that, but I think that what you're saying is actually going to work as well. Resonance. Good call. Polar refers to the distribution of electrons, but this is going for that shifty bond. For example, if you've got something like ozone, ozone is 3 oxygens. So if we take a look, 3 times 6 is 18. We would end up with 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. If we have, we don't have 20 in this case. If we have more electrons in our drawing than we have, we've got to get rid of 2 and draw a double bond. Now the question with that is, the atoms are remaining in the same place. The electrons are being redistributed a little differently. This is one way we could draw that. And the other way would be with a double bond on this oxygen instead. Nice call, Ryan. Here on this guy right here, if we take a look, when we draw this out, if you had this as a lone pair for the carbon, that would give the carbon a different formal charge. So remember, to find the formal charge, you take the element. Carbon is in group 4, so we have 4 minus 1, 2, 3, 4 bonds. That would be 0 for that carbon. If we had this oxygen over here, it would be 6 minus 1, 2, 3, 4, 5, 6. So that would be 0. This oxygen up here, we have 6 minus 7, so that's negative 1. This oxygen down here, 6 minus 7, so that's negative 1. That's what gives us an overall of negative 2. The best structure you can draw is going to have your formal charge as much as 0 as possible. The way this will be tested is you won't have to draw because it is on canvas. What you will have to do is it'll say, okay, find the formal charge of this atom if it's under these circumstances. For example, what if we have selenium and the selenium is bonded to 4 atoms and has 1 lone pair, you would have to look and find the group number for selenium and then subtract 1, 2, 3, 4, 5, 6 from that to see what selenium's formal charge is. Which structure would have a pi bond? Remember, a single bond is the one single handshake. The pi bond is any other bond after the first one. So this has just the sigma bond or a single bond. This has a sigma bond and a pi bond. And remember, in a double bond, that's the handshake up front for the sigma bond, and the pi bond is that perpendicular, like side hug, that overlapping. That occurs between p orbitals. That overlapping, that pi bond, occurs with p orbitals. And basically, they come around the side. They're not directly on. They're more perpendicular. Which one has resonance? Well, this double bond here, we could have drawn on either of these guys. So this one would show resonance. Remember, that's the same thing that this question up here asked about. Referring to the above, describe the shape. We already have all the sp3 stuff. So referring to the above, describe the shape of CH2Br2. So this is sp3 hybridization with no lone pairs. So the shape is the same as the arrangement, tetrahedral. For this one right here, it is sp3d1, which would be an arrangement of trigonal bipyramidal, but this shape is seesaw. Oops, wrong C. The SCO3, we have sp2 hybridization, which means that we're looking at trigonal planar for the arrangement, and since there are no lone pairs here, trigonal planar for the shape. Electronegativity differences. If we look at O and P, we're going to take 3.5 minus 2, so that's by minus 2.1, so that's going to be 1.4, I believe. I don't have my watch on today. 1.4 is, remember, we go from 0.4 to anything 0.4 to 2. Anything in this range right here, between 0.4 and 2, that is polar covalent. 0.4 or less is nonpolar, and 2 or above is ionic. So this would be a polar covalent bond. P and H, 2.1 minus 2.1 is 0, so that would be 0.4 or less. So that's a nonpolar covalent bond. O and K, that's going to be over 2. 2 or above, so that's going to be an ionic bond. Again, the ionic is when you take the electrons. The polar covalent is when there's an uneven sharing, and polar covalent is when there's a perfect handshake. So there is a difference between polar bonds and polar molecules. First, you got to find if the bonds are polar, and then you have to look. So this is telling you it's linear. So that means that the oxygen is going to have the higher electronegativity between itself and Si. So the oxygen is going to get a pool of the electrons towards it, and this oxygen is going to get a pool of electrons towards it. Even though these are polar bonds, they cancel out. So that would be a non-polar molecule. Here we have OI2, which is bent. Again, these are polar bonds. We can see that by these dipole arrows. So everything is going towards the oxygen, and nothing is forcing it this way, downward. So that is a polar molecule. Here we have Cl, N, and F. It is trigonal pyramidal. So that means that we do have this lone pair on top, which is going to have no pool. It's F2, so we're missing an F here. Since there's a pool in directions of these two, and there's nothing for the Cl and nothing for the lone pair to pull on, that's going to pull the electrons closer to the Fs, making that molecule polar. Don't forget, you'll want to review bond energy whenever you subtract these bond energies from each other. Remember, that is bonds broken. Oops. Bonds broken minus bonds formed. So this is the amount of energy it takes to break these bonds. This is the amount of energy that is released when these bonds form. Right? So that's why we take the amount of energy required to break them minus the amount of energy that's released when they form. That gives us whether it's endothermic or exothermic. If it's negative, it's negative, it's exothermic, and if it's positive, it's endothermic. Remember, it takes energy, cannot be created or destroyed. So the amount of energy it takes to break a bond is the same that's released whenever it's formed. Questions? I'm going to stop the recording if you're worried about being recorded.